Okay, so here's where we're going to look at RLC series circuit, and then we're going to look at what's involved in bringing it to correction or bringing it to a unity power factor or a PF equal to 1. That is going to be one where our apparent power S equals P, our phase angle is 0, and it means that it's the load as a result after correction is going to be equivalent to a purely resistive circuit. But really, in order to start this whole thing, let's not even go as far as even considering correction right now, and simply think of all of our processes or methods that we put in place when we're working with an RLC purely series circuit. And first of all, it really comes down to the impedance triangle. And when we look at the impedance triangle that's found by simply adding up all the individual values of opposition, that's really important because through the impedance triangle and your common current, it leads you into voltages for a voltage triangle and a power triangle when you look at the common current being squared and multiplying by each value of impedance to give you your power. When you look at the common current I total multiplied by each value of impedance to give you your voltage triangle, any RLC series circuit analysis should really start by the impedance triangle and using that total impedance to determine your current, and from there following through that process. And it's really not that difficult once you just boil it down to a common way of approaching purely RLC series. So let's take a look at this example. So I've started out with an RLC and given it values of both reactance and resistance. Of course, if this was an example of a circuit that was including an L value and a C value, you'd have to go through the proper equations to determine XL and XC. In this case, we've given those values to kind of avoid that step and concentrate on what's important here. So let's just give this VS a value here as well, and we'll just go with our typical 120 volt VAC source, okay? Now, coming back first of all to just the impedance, which is all we're worried about, notice how I've shown the opposition phasors here of R at 0, which of course would be our resistance, and in this case 130 ohms. I've shown the plus J XL, and that's part of this understanding is we need to understand when it comes to the value of inductive reactance, it's always a plus J component. So we have our plus J component as our total value of 100 ohms here. But then we have some XC as well, which is a minus J component that makes up this, this impedance or total impedance. Now remember, because we can add these all up, it's as simple as saying Z total would equal R plus J XL plus minus J XC. What it means is then you've got a overall imaginary component or J component from these two values, doesn't it? And they would equal what would be referred to as your net value of reactance, right? It's a plus J added on to a minus J, which at the end of the day is equal to XL minus XC, okay? All right. So knowing that then, and when we look at our impedances here, we know that our overall impedance is going to be found by our 100 ohms of plus J added on to our negative value of 25 ohms, which is why I showed the minus J added on here to give you the total. That's our total, or that's our X net value, isn't it? Our X net value is equal to 100 plus minus J 25, which is going to be the result of 75 ohms of net reactance, okay? So now if we turn that into a triangle, that means that what you would do is you'd have 75 ohms of plus J over here, so this would be plus J 75 ohms of net value, 130, and that's going to give you your impedance triangle. Okay, so now that we've seen how we built that impedance triangle, in order to kind of simplify things, I'm just going to do some erasing here, and so we're concentrating on the impedance triangle and the impedance triangle only. Okay, so what I did is I just removed some of the clutter. I illustrated previously how we come to this in terms of illustrating each one of the opposition phasors in a diagram, and that leaves us with an impedance triangle. The values directly from a series circuit can be put into an impedance triangle because it's series. We know we just add the oppositions together. When we do that with a parallel circuit, what we're doing is showing an impedance triangle, which is showing the series equivalent of a parallel arrangement. So, knowing that then, what we have is this is our impedance triangle. We can say from this triangle alone that the rectangular value to represent total impedance is Z total equals 130 ohms plus J 75 ohms, right? Now, that's our rectangular value. If we want to come up with the polar value, that's going to give us the hypotenuse of our triangle, which is our total magnitude of impedance expressed as a polar value. And we will be able to get an angle. So we're going to just convert to polar. So that's going to be 130 plus J 75 converted to a polar value is going to be 150 ohms, and I'll make that 150.08 to follow 2 decimal places, 150.08 ohms, and then we're going to put our angle in here, which is going to be our angle of impedance. Okay? And our angle here happens to be 29.98. 29.98 degrees. Okay, so that's our angle of impedance. Remember, when we divide our impedance angle into our source voltage, that's going to give us our phase angle. And remember, dividing into there is going to give us an opposite angle, which is going to indicate a lagging current. And that is consistent with the fact that this circuit is primarily inductive. How do we know it's primarily inductive? Because XL is our largest opposition, or our largest impedance connected in series. Okay, so this is going to mean that we could otherwise express this as 150.08 ohms at an angle of impedance, phi or phi, that would be 29.98 degrees. Okay? Now, knowing what we know about purely series then, I total equals IR equals IL equals IC. That means our common quantity of current, when multiplied by each one of these values, is going to give us I total times Z total, which we know is V source, I total times R, which we know is VR, and I total times X total. Remember, that's our total amount of reactance, is going to give us our net voltage in this circuit, right? Now, understand that the two individual voltages, when added together, are going to give you this net voltage. So this is just indicating the net reactive voltage in this circuit, okay? So it means that when we add these all together, that should equal the applied voltage. So we can start by determining our I total value. So I total is going to equal V source divided by Z total. And now we're just going to do the magnitude for now, because we know all the angles. So we're going to just do the magnitude. So that's going to be 120 divided by 150.08. That's going to result in a current of 0.798 That's actually going to be 0.8. It's going to round off to 0.8. So I'm going to show two decimal places. It's going to be 0.80 amps. Okay. So now that we have our current, we know that our current multiplied by each one of these values is going to give us our voltage triangle, right? So if we want to say that we take our I total times R value, that's going to give us our resistive voltage. If we go I total times our X net value, that's going to be the result of VL minus VC, if you were to verify that, and then I total times Z total is going to give us our source voltage, okay? So I'm not even going to actually do that because you can verify that if you like. It'll all work out, proving Kirchhoff's voltage law and things of that nature. But what I'm going to do is I'm going to move to power next, right? Because that's really where we're going with this, power factor correction. The rest of this is just our simple RLC series circuit analysis that we've talked about. So what it means then is if we now use our common current once again, which makes sense, right? We're working with a series circuit. I've always said that when it comes to series circuits, current becomes your common quantity that you use for design, analysis, and so on, and it's no different here. So it means that our I total squared value is a common approach to determining our powers now, both our real and reactive power. So I total squared times Z total is going to equal S total. That's going to equal our total VAs, right? I total squared times Z total is going to equal our total VAs. So this will equal S total, right? Over here, I total squared times X total is going to equal our QL net value. So I total squared times X total. Remember, X total is the result of XL minus XC equals our QL total here. And why do I say QL? Because it's primarily a plus K component. So that's why I said QL as our total value. Now, you only have left the watts, or the real power. So then you have I total squared times R to give you PR. Okay? So that's important because remember, after we've come up with that, we'll have all of our reactive power, our total reactive power, one that comes from QL minus QC. We'll have our total real power, and we'll have our total S value of our VAs. Notice how that's going to result in, because it's all the same value of I total squared, that's going to result in a power triangle with the exact same proportions that we have here and the exact same angle, right? So that means that our power factor in a series RLC circuit can be found by the impedance triangle only. Without even looking at an applied voltage, if I just gave you this series arrangement, you could tell me what the power factor would be for this load connected to any source. And how would it be determined? By the impedance triangle, coming up with the angle of impedance, and now power factor is going to equal cos theta, where the angle here is 29.98. So that means if you were to do your power factor, that'd be the cos of 29.98, and in this case that would equal 0.87. So this would be a 0.87 power factor. Okay, so what does that mean? That means that now as we go about adding correction, we want to correct this 0.87 power factor and bring it up to a value of 1.0, right? So we're going to change that 0.87 to a unity power factor. Now, here's the thing we need to understand, and then I'll do some erasing and we'll go at it here. So, when it comes to correcting an RLC series or even a combination circuit, we have to understand that everything that makes up that load, either in purely series or in a combination of series and parallel, that's what's representing the load, right? So inside the dotted line here is the load, right? So this could be a plant, a factory, just a building with transformers, motors, inductive loads. So it's a plant, factory, or building. This represents the whole building load. And our correction always happens as a correction capacitor right across. Now remember, this was 120 volts VAC, right across the source. So this is where a correction capacitor goes every time, regardless of how the load's connected. Right across the source, right across the load to correct it and bring it to unity. So I'm going to pause it here, do some cleanup, and then we'll come back and approach this as power. Okay, so I did some erasing so that we removed a little bit of clutter here, and now we're moving into power. Remember, this power triangle is all based on back to the same old impedance triangle. So what I did is I just included the values of impedance here in smaller form, and we'll now convert this all to power. But remember, the angle here in the impedance triangle is going to be the same angle for the power triangle. So what do we have here? We have a value of R, 130, a value of total X net, 75, and a value of total impedance of 150.08. Okay, so notice how here we're using our I total squared value as the common current squared to multiply by each one of those impedances. That's going to give us power, right? It's series. It makes the most sense to follow through with I total squared. If we're looking at parallel, we're using V squared over R, V squared over XL, V squared over XC. Okay, so if we go here with I total times Z total, then I total squared times Z total, that's going to be 0.8 squared, because remember that's what we had for our current was 0.8. So 0.8 squared times 150.08, 0.8 squared times 75, and 0.8 squared times 130. Okay, so let's start with our total S. Now remember, this is going to be our S value, our VA value. So that's going to be 0.8 squared times 150.08. That's going to give us 96.05 VAs. 96.05. Unit is VAs, and we know the angle of those VAs is 29.98. Now, what we're going to do is get our value of QL net. QL net is going to be 0.8 squared times 75, giving us 48 var. Okay, so that's our 48 var value, and now we move on to our PR value. So that's going to be 0.8 squared times 130, giving us 83.2 watts. Okay, so there's our power triangle. And remember, this resulted in a power factor of, I think it was 0.87, right? So 0.87 then would be 83.2 watts over 96.05 VAs to give you a power factor of 0.7. It's the result of 48 var of inductive reactive power. So what's our purpose of bringing in this correction capacitor? To introduce 48 var of minus J in order to bring this down to zero. If I add 48 var of minus J, that's going to bring this Q net value to zero. And because of that, that means that everything will be our real power, our 83.2 watts of dissipation once I do this. Okay? So I'm going to now let's hold on to that value of 48 bar. You can always rewind the video if you need to here, because I'm going to pause it. I'm going to get rid of this clutter again, and we're going to attack this 48 bar that we need to remove for our power factor correction. Okay, we're back, and what I've written up here is our QL net value from our previous calculations, and our power triangle was 48 bar. So that means we've identified the number of VAR required to bring this to unity. We need to have QC equal to 48 VAR. We need to introduce 48 VAR of QC. And where's that going to come from? It's going to come from this capacitor connected right across the source. And now this is where our approach changes, right? Because here, based on the fact that it's right across the source, we're going to be working with QC equals Vs squared, the applied voltage squared, over XC, okay? But remember, in order to come up with the value of C needed here, we need to move forward with determining the value of XC in order to use 60 hertz and that way figure out the value of C in farads. So where do we go next after we have this? Well, we're looking for a value of XC, so we're going to say XC is equal to Vs squared over QC. So in this case, that would be 120 squared over our QC value of 48 VAR, right? So 120 squared divided by 48 means our XC value has to be 300 ohms. Okay, so 120 squared, our applied voltage squared, Vs squared, divided by our QC value, which we know needs to be 48, is 300 ohms. Okay, so where do we go next? Well, we know that when we look at this value of XC, that's equal to 1 over 2 pi FC, but it's the C value we want, so C is going to equal 1 over 2 pi F XC. And if we move forward with this, we know for 60 hertz that's 377, and we know here we have a value of 300. So our C value is going to be 1 over 377, the angular velocity for 60 hertz, multiplied by now our XC value of 300, and that's going to give us a C. So 1 divided by 377 times 300 means that we have a value of 8.84 microfarads. 8.84 microfarads. Just going to double check my decimal places here because I have to move it 6 to the right. And so yeah, that's 8.84 microfarads. So that means our value of correction here would be 8.84 microfarads, of which we know when connected across 120 volts AC, working backwards, that's going to give us our 48 bar. So the last thing I'm going to do is just show another description of this circuit as the power components, just to give it its final kind of illustration, and then that should be it. So I'll pause it and then do that, and we'll come back to that. Okay, so here's the final kind of illustration here, and this is where we broke down each one of these components into its real or reactive power and drew it as it's configured with a series arrangement and a parallel arrangement to 120 volts. And remember, for all power, doesn't matter how it's connected, once you have the power values, whether it be reactive power or real power, or even value of S for that matter, you can add them all up to determine the total power value. So notice how here, how did we come about that PR? Well, that was our value of current through this branch squared and multiplied by 130. If you wanted to rewind, you would see that's 83.2 watts of real power. If we look at our individual L value here, now remember this, we came up with a net value of bars here, but let's look at the individual value of bars to make some sense of this. If I take 0.8 squared, which was my current, and multiply it by 100, I get 64 bar here, and then I do 0.8 squared and multiply it by 25, I get 16 bar here. Notice how these are plus J bars and minus J bars. Together they equal a total net reactive power of 64 minus 16 to give us 48 bars. And this is what made our load power triangle, didn't it? Remember, this is our plant, our building, or our factory inside of this dotted line. And this is where we brought our PF correction, didn't it? We brought our capacitor in to correct this, and what did we find we were working with? We found we were working with a total value of 48 plus J bars that had to be corrected with 48 bars of minus J. How do we calculate the C value of 8.84 microfarads in order to give us that? We understood that it was connected right across the source, so we were using a V squared over XC as our approach to determining that value. So that's really it, guys. That would mean that now we would have a total VA equal to our PR now, right? Now that we have a PF equal to 1 in this circuit, our S would equal our P. So that would mean we have a corrected circuit. Okay, I think that's really all I wanted to go over as far as this goes, is to really break down that approach step by step.